Assalamualaikum and selamat sejahtera. Today, our group that consists of these group members will be presenting about the applications of operational amplifiers, also known as OP, AMPS in short.
So, what is an op-amp? It is a short form of operational amplifier, and we can see its official definition and basic schematic symbol. Simply put, an op-amp is a high gain voltage amplifier that features two differential inputs. We have two differential inputs labeled as V plus, the non-inverting input, and V minus, the inverting input. At the top and bottom, we have a Vs plus and a Vs minus, which provide the necessary power supply to the components. And finally, on the right, we have our single output voltage. What makes an op-amp so special and widely used are its four key features. High voltage gain. It can immensely amplify a tiny difference between its input. Secondly, differential inputs. It amplifies the difference between the plus and minus terminals. Third, high input impedance. This ensures it draws virtually no current from the input source, preventing it from loading down the previous circuit. Fourth, low output impedance. This allows it to efficiently deliver a strong signal to the next stage or load without dropping voltage. Ultimately, its core purpose is to amplify, process, and condition electric signals so they are usable for electronic system. Now we know what it is. Let's talk about why it matters. To truly appreciate op-amps, we have to look back at historical needs. Before modern digital computer existed, engineers faced a massive challenge. They need a reliable hardware device capable of performing mathematical operations directly on electrical signals. This is actually where the name operational amplifier comes from. Originally, these analog components were engineered to perform complex calculus and arithmetic operations in real time, such as addition and subtraction, and integration and differentiation. While digital microprocessors handle most computational today, you might ask, why is the op-amp still so critical in modern electronics? Well, the physical world is inherently analog. Because of this, op-amps remain indispensable today for four main reasons. First, they amplify weak signals. Think about a tiny biosignal from medical equipment or faint data from environmental sensor. Op-amp boost them to level a computer can actually read. Secondly, they improve measurement quality by filtering out unwanted electrical noise. Third, they enable advanced signal processing, allowing us to shape and filter audio, radio, and video signals. Fourth, they support control and automation systems, acting as the bridge between raw analog sensors and physical actuators in industrial machinery and automated systems.
So who uses op-amp? Electrical and electronics engineers rely on op-amps for designing analog circuit. Key industries include telecommunication, medical device, consumer electronics, and instrumentation. Academic and research institutions use op-amp extensively for prototyping, experimentation, and advancing signal processing technologies. Op-amp was first developed in 1941. At that time were called vacuum tube or summing amplifier, made by Carl D. Schwartzel Jr., used in World War II in military analog computer for artillery targeting, improving accuracy against V-1 bombs and aircraft. It was later on improved multiple times until a global standard op-amp called the Unstoppable mu A741, which was the breaking point of op-amp evolution, and which is still manufactured and studied today.
Next up is where OP-AMPs are applied. It is applied in analog signal processing such as amplifiers, filters, and oscillators. It is also used in consumer electronics such as audio amplifiers and sensors, for industrial control systems and instrumentation as well. It also used in medical equipment including electrocardiogram, ECG, and electroencephalo or EEG machines that measure very small electrical impulses.
So how exactly do operational amplifiers or OP-amps work? At their core, they rely on a differential input stage that takes the voltage difference between two inputs and massively amplifies it. Internally, this happens across three main stages: the differential amplifier, a voltage amplification stage, and finally the output stage. But because the internal gain is too high, we use negative feedback to tame it. This gives us control, boosts stability, and cuts down on distortion. By changing how we route this feedback, we can build different configurations. For instance, a non-inverting amplifier scales the signal using the formula R1 plus R2 over R1. An inverting amplifier flips the polarity with a gain of R2 over R1. Or we can create a voltage follower which keeps the gain at exactly 1 to buffer the digital perfectly. Now that we know how they work, how do we actually use them? In practical application, OP-amps are incredibly versatile. Take the voltage follower, which acts as a buffer. It keeps the output equal to the input while isolating signal using high input and a low output independence. We can also use them to scale signal. An inverting amplifier flips the polarity and scales the output based on the resistor ratio, while a non-inverting amplifier keeps the signal in phase, making it perfect for high independence source. Finally, we can do complex math and logic, integrator and differentiator. Let us generate waveform or detect signal edges by tracking rate of change. And comparator allow us to contrast two voltage, giving us a simple high or low voltage digital.
Next, we move on to the example application of operational amplifier. So one of the example is audio amplifier, which is amplifying audio signals with minimal distortion. Alright, an operational ampere based audio amplifier boosts weak audio signals to drive speakers or headphones. Using a non-inverting amplifier configuration, the gain is set by two resistors, and negative feedbacks ensure low distortion and stable output. Benefits include improved sound quality, precise volume control, and wide frequency response, making operational amperes ideal for hi-fi audio, mixers, and portable devices. Another example that has operational amplifier is sensor signal conditioning. It amplifies and stabilizes the sensor outputs. Alright, operational amperes are commonly used to condition weak signals from sensor before they reach measurement system. Key functions include amplifying low voltage output, filtering high frequency noise, and stabilizing signals for accurate reading. A typical example is temperature sensor signal conditioning, where an operational amplifier amplifies the small voltage from a thermocouple or RTD, applies a low pass filter to remove noise, and deliver a clean scale signal to a microcontroller or data acquisition system. For summary, let's recap operational amplifier. So, what are the operational amplifier? Operational amplifiers are versatile, high gain differential amplifiers, and it is essential for precision and flexibility in analog circuit. Who use it? electrical engineers and industries worldwide rely on them, and even mechanical engineers also can use them. And it is popularized since the 1960s and still be used until today. And we commonly can find the example of operational amplifier in audio, mechanical, medical, industry, and consumer devices. And it operates via differential amplification and negative feedback. So that's all from our group. Thank you for listening. Thank you for take your time to watch our video. I wish you have a good day.